Because in terms of problem solving, okay, now this one is a standard problem. So this is one of the problems that you will have to focus on. You have to practice this because you guys are getting into engineering. Okay, so this is important. This is a standard problem. All right, so if you have two cylinders, one solid, this one is going to be solid, the other one is going to be hollow cylinder. All right, so this one is solid, this one is hollow. If you roll them down, would they reach the ground at the same time? Will they have the same speed? All right, let's get something on mathematical prediction first. And then we'll check to see if that prediction makes sense. We'll do real science, man. This is what we do here. All right, so which one is going to reach the ground sooner? All right, so here's initial height. They're at the same height. Ignoring friction, air friction, mechanical energy is going to be conserved. The surface friction is going to be responsible for the rotational motion. So you cannot ignore the surface friction, but that surface friction is not putting the brakes on the system. Okay, so it's not going to change the mechanical energy. It's just causing rotational motion. All right, so the mechanical energy is constant. Initial mechanical, final mechanical energy. Mechanical energy is a combination of kinetic and potential energies. Kinetic energy is going to be a combination of translational kinetic energy and rotational kinetic energy of these masses. All right, so we got our translation, rotational, and kinetic energies as well as the potential energy terms. All right, so it looks kind of nasty, but it's not. Initial velocities will be 0. The final height is going to be 0. And now let's come up with an expression for the final speed. So omega can be expressed in terms of the tangential speed or the translational speed. All right, so omega, let's express it in terms of the tangential speed. So I'll do a back substitution. So what else do we have that we can use? We got mass here. We got a rotational inertia here. So rotational inertia, I was going to take a shortcut. I don't want to. All right, so factor out the speed. I think that makes sense. Get rid of 1/2. Just go after the speed at this point because I want to come up with a generic expression first. It's going to allow me to make some predictions. All right, so get rid of the square. Okay, now we're ready to make our first prediction. Okay, are they going to roll at the same rate? Are they going to have the same speed at the bottom of the incline? It depends. Do you think we'll have the same moment of inertia? Hollow cylinder versus solid cylinder, are they going to have the same moment of inertia? Not really. They're not going to have the same moment of inertia. All right, one with a larger moment of inertia is going to be moving slower. Hollow cylinder is going to have a larger moment of inertia, so it's not going to move as fast. Guys, moment of inertia is the resistance to change in rotational motion, resistance to rotational acceleration in this case. So one with larger moment of inertia is not going to move as fast. Solid cylinder is going to have a small moment of inertia, which means that solid cylinder is going to end up moving faster. Okay, so we end up getting that prediction, so which means that we should be able to take this math to its conclusion because there's something else which is interesting. So they're not going to be accelerating at the same rate. They're not going to have the same final velocity. So how can you figure out what g is if the speed of the object depends on the geometry, whether or not it's hollow, or whether or not it's hollow or solid? And so this becomes a problem for Galileo, obviously. Of course, at the time Galileo was doing this, the math wasn't that sophisticated. I wonder how he overcame it, but we'll stick to our little math and then continue. So in terms of the hollow cylinder, you look up, check to see what the moment of inertia is. So it's going to be mr squared. We'll do a back substitution. And then something interesting starts to happen in mathematics. I'm just going to let algebra work itself out, like terms will cancel. Oh, math is not going to matter, so that's interesting. Boom. It's not going to matter. All right. So from Galileo's perspective, we're done. All right. So from Galileo's perspective, I'm going to let's get back to the last equation. I just want to stop this one. This is where we stop. Okay. Somehow he was able to calculate the final speed. Okay, because he knew the interval within each and every single time interval, 1 unit of time interval, you would get 1 unit of distance, 3 and 5, and so forth. So he knew how to calculate the final velocity. He knew the initial height, and from that he was able to calculate g. So which means that the experiment that he devised would allow him to actually figure out the gravitational acceleration. So this is for the hollow one, and notice that the mass of the object doesn't matter, just like in free fall. Okay, now we got a solid cylinder. Oh, we got solid cylinder, so it's gonna have its moment of inertia is gonna be half of that the hollow one. So I becomes 1/2 mr squared. Okay, r squares will cancel obviously. We need to have a common denominator here, so what is it? It's gonna be 3/2. Okay, mass will not matter at this point. So this is going to be the speed of the solid cylinder. This is the hollow one, and this is the solid one. Notice that solid one is going to move faster than the hollow cylinder. Once again, masses won't matter. It's a cancellation of the masses. So what determines the speed is obviously this hollow mass distribution. Let's say it's not the mass itself with respect to the point of rotation, which is the moment of inertia. Depends on the initial height, depends on the value of g. This one is going to be faster. We got our predictions on that one. So what does that look like in real life?
In motion with a motor, and because there's frictions in the bearings, but it's a ring, and the other is a piece of wood. Now, if these have the same mass, they have the same inertia, but they don't have the same rotational inertia because that mass is distributed in a different way. For this, the mass is distributed uniformly throughout. For the ring, the mass is all distributed far from where the axis of rotation will be, which is going to be right through the center. And so this will have a greater rotational inertia than this wooden disc. What we're going to have them do is race down this incline. And the one with the greater rotational inertia will lose the race because it will have a greater resistance to a change in its state of rotational motion. Now, right now, the state of rotational motion of both objects is zero. They're not rotating. Once I remove the piece of wood.
All right, so the rotational inertia of the hollow disc is going to be larger than the solid disc, right?
One of them is going to rotate more quickly. Let's see which one that is. So the wooden disc rotated more quickly and won the race down the incline. That makes sense because we said that the metal ring had greater rotational inertia, so there's a greater resistance to a change in its state of motion. It's going to have a smaller rotational acceleration as it goes down the plane. Let's take a look now at our disc. You can see that it's still turning. It's slowing down. It's almost a state of rotational motion. Now, rotational inertia than this wooden disc. What we're going to have them do is race down this incline, and the one with the greater rotational inertia will lose the race.
Okay, so the question is, how come this is a greater rotational inertia? Okay, guys, that's called the derivation. I will do at least one single derivation for you guys. Stuff that you've seen on the tables, obviously there's a way to figure that out. It requires a little bit of calculus, obviously. All right. Conceptually, why is it that it has a larger rotational inertia, moment of inertia? Remember, guys, the moment of inertia depends on where the mass is and its radial distance to the point of rotation. Notice that the entire mass is concentrated at a constant radial distance away from the mass. All right, so this is going to have a moment of inertia larger than the other one. Both of them have the same mass. Notice that the distribution of the mass for the solid one is uniform, not all the mass at the perimeter. So which means that the moment of inertia is going to be smaller for that one. Moment of inertia, rotational inertia, in this case represents the resistance to rotational acceleration. All right, so the more it resists to rotational acceleration, the slower it's going to move. All right, so that's what happens.
Because it will have a greater
that's what happens to the
resistance to a change in its state of rotational motion. Now, right now, the state of rotational motion of both objects is zero. They're not rotating. Once I remove the piece of wood, one of them is going to rotate more quickly. Let's see which one that is.
All right, so that worked out. All right, so we got the best answer. All right, so the best answer is going to be C, right? So C is the best answer. For every single correct answer, give yourself 5 points. All right, let's do a fast lecture review. Lecture review, the faster one. Okay. Oh. Okay, what else? Done with that one. Okay, so all right, so question number 17. So you got a pilot exposed to 12 G's of acceleration. So what kind of acceleration is that? That rotational average, centripetal, tangential, or total acceleration? It's going to be total acceleration, just like that. So it's going to be a combination of centripetal as well as the tangential accelerations. All right, so what's the relationship between the moment of inertia and the radius? Moment of inertia is going to be proportional to the square of the radius. What's the relationship between the moment of inertia and mass? Is going to be a direct relationship. Rotational mass depends on the regular mass. All right, so which is easier to swing or get swinging, a baseball bat held at the end or and closer to the mass man? Okay, so okay, so this looks like a baseball bat. I'm an artist. Okay, so here's the mass man. This is the regular end. All right, so mass end, this end is going to have a larger mass. So this end, if you're swinging it from this end is going to be larger. It's going to be more massive. So this is the distance to the more massive end. So which means that the moment of inertia of this is going to be bigger. So which means that it's going to be tougher to swing this, holding the handle here versus the other one. Okay, this end is going to be less massive, the same distance. So the moment of inertia, rotational inertia of swinging it in this direction is going to be easier. So less massive end is going to be easier from the less massive end. This end is going to be easier to swing than the more massive end. Man, that was a tough thing to explain. All right, so the rotational kinetic energy, boom, 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 it's related to rotational velocity. Okay, so which one will have a greater acceleration rolling down an incline, a bowling ball or a volleyball? Down the derivation for a rolling cylinder. Okay, so the mass is not going to matter, guys. Volleyball is going to have a larger moment of inertia because all its mass is going to be located at the same radial distance away from the point of rotation. So, which means that bowling ball is going to have a smaller rotational inertia, so it's going to actually move much faster. All right, so we are done with that.